Welcome to The Explainer. I am super excited to have you here today because we're unpacking one of the most fundamental, honestly kind of mind-bending concepts in data science. We are focusing on topic 5.5, which is regularization. Basically, it's all about how we keep our machine learning models from getting, well, literally too smart for their own good.
To really grasp why we even need regularization, we first have to understand the monster it was built to fight. So, what exactly happens when an AI is too smart for its own good? Imagine you've got a student prepping for a massive final exam, but instead of actually learning the underlying concepts, this student just memorizes the exact answers to the practice test, like every single one of them. On that practice test, they score a perfect 100%. But then they sit down for the actual final exam, the one with brand new questions, and they fail miserably. Why? Well, because they just memorized the specific quirks of the practice data rather than learning the generalized rules. In machine learning, we call this phenomenon overfitting.
Okay, let's dive into this visually. Imagine a graph where the dark dots represent our training examples, our actual data. Now picture a machine learning model trying to fit that data, specifically a super complex polynomial of degree 15. The line it draws desperately twists, turns, and contorts itself just to hit almost every single dot perfectly. At first glance, it looks like an amazing fit, right? Nope, wrong. The model is literally just memorizing the noise, the little sampling imperfections, and the random quirks of this specific dataset. If we were to throw new data points at it, the actual exam, that wild, spiky line would wildly miss them. It has absolutely zero ability to generalize.
Part 1. Introducing the hero. Regularization.
So how exactly do we stop our algorithms from acting like that overly anxious, memorizing student? Well, enter our hero, regularization. Now, it's not just one magic trick. It's really an umbrella term for a whole family of methods that deliberately force a learning algorithm to build a less complex model. You can think of it like a mathematical leash. When an algorithm starts getting a bit too carried away, building these incredibly complex, multi-dimensional formulas just to flawlessly predict the training data, regularization yanks on that leash and says, hey, nope, keep it simple. It actively restrains the model from learning all that distracting noise in the data. But how does it actually pull that leash? It hits the algorithm where it hurts, the objective function. Normally, a machine learning model just wants to minimize its errors, no matter what. But with regularization, we tweak that objective function by adding a penalty term. And the rule is super simple. More complexity equals a higher penalty. So if the algorithm starts assigning huge, complicated weights to different features just to perfectly hit every single data point, the penalty absolutely skyrockets. To win the game, the algorithm is mathematically forced to balance being accurate with being simple.
Part 2. The core philosophy, the bias-variance tradeoff.
We are essentially talking about the bias-variance tradeoff here. Think of these as two opposing forces. Variance is our enemy from earlier, overfitting. It happens when our model is highly sensitive to tiny fluctuations or noise in the training data. Bias, on the other hand, is underfitting. That's when our model is just a bit too simple to capture the true underlying relationship, kind of like trying to fit a rigid straight line through a U-shaped curve. So, the crucial point is this. Regularization intentionally introduces a tiny bit of bias, just a little bit of imperfection, in order to massively reduce variance. We accept that our model won't perfectly memorize the training data because, honestly, that's exactly what stops it from making wild, unpredictable errors on brand new data.
But you might be wondering, how much penalty is the right amount? Well, that's where the hyperparameter C comes into play. Think of C as a dial on a stereo that controls the strength of the regularization penalty. If you turn that dial all the way down, so C equals 0, the penalty is turned completely off. You're just back to a standard model that's highly prone to overfitting complex data. But if you crank that C value way too high, the penalty becomes so extreme that the model is basically terrified to learn anything at all. It gets overly simple, risking severe underfitting or high bias. The true art of data science, really, is tuning this C dial to find that perfect Goldilocks zone, where variance is reduced without crippling the model's actual predictive power.
Part 3. The arsenal. L1 versus L2 regularization.
Now, what's really interesting about this slide is the distinct personality of each method. First, we have L1 regularization, also known as Lasso. I kind of like to call L1 the ruthless editor. If L1 decides a feature isn't absolutely essential for making a prediction, it just forces the mathematical weight of that feature to exactly 0. It literally deletes it from the equation. This creates what we call a sparse model. It's incredibly useful for automatic feature selection, which gives us a really clean, easily explainable model. Then on the flip side, we have L2 regularization, or RIDGE. L2 is more like the diplomat.
Instead of zeroing things out entirely, it just shrinks the parameters, pushing them really close to zero, but rarely deleting them completely. Because L2 is mathematically differentiable, it plays very nicely with optimization algorithms like gradient descent. That makes it generally better if your main goal is just maximizing raw predicted performance on new holdout data.
And while we often use linear regression to explain these concepts because, well, it's pretty easy to visualize, regularization is literally everywhere. You can actually combine L1 and L2 into something called elastic net to get the best of both worlds. Plus, modern neural networks, which are basically giant engines of complexity, absolutely rely on L1 and L2 to keep their millions of parameters in check. They also use advanced neural network-specific tactics that act as regularizers. Take dropout, for example, where we literally switch off random parts of the network during training so it can't over-rely on any one single pathway. Or data augmentation, where we slightly alter training images to artificially expand our data and prevent the model from memorizing exact pixels. It's fascinating stuff.
Part 4. Making models useful.
It all really comes back to a single, unifying goal, and it brilliantly illustrates our entire journey today. The famous statistician George Box once said, "All models are wrong, but some are useful." Think about that in the context of everything we've just covered about regularization. Without it, an overfit model tries so incredibly hard to be 100% right on the training data that it becomes completely useless out in the real world. Regularization is the tool that deliberately makes our models a little bit more wrong on the training data, introducing that tiny bit of bias just so they can be infinitely more useful when faced with the messy, unpredictable reality of brand new information.
Ultimately, by letting go of this need for perfect memorization, we actually achieve true learning. We stop memorizing the noise, and we finally start understanding the signal. So, as you head out to tune your own algorithms and twist that hyperparameter dial, I want to leave you with this thought. By intentionally accepting a bit of imperfection, what useful truths will your next model uncover? Thanks so much for joining me on this explainer, and keep exploring.